Thank you very much for having me. So let me start clarifying the title of the paper. Yeah, so it comes from a quote by Olivier Blanchard, in which from an essay in which he kind of gives his view on what we as economists should have learned from the crisis. Okay, one point he emphasizes a lot is the importance of non-linearities. So in particular, in his view, a large shock to the economy can have quite different effects than sort of a regular small business cycle shock, and specifically a large shock may bring the economy into some kind of a danger zone in which very bad outcomes may become possible. So what comes to mind is like a very large and persistent increase in unemployment, perhaps like we've seen here in Spain. Okay, so now one way to kind of formalize this very sort of nonlinear view of the world that Blanchard seems to have in mind is to write down a model with multiple steady state rates of unemployment. So I'll talk about the labor market today. So that's illustrated by this figure here. So here we have UT on the horizontal axis, unemployment today, and unemployment tomorrow on the vertical axis. So this illustrates a model with a single steady state. So this solid black line gives you the relation between unemployment today and unemployment tomorrow, and here we have this intersection with the 45-degree line where unemployment tends to remain constant. So that's a long-run steady state. Again, we will kind of follow the dynamics that's implied by this line. We see this is really a long-run tractor here. So this is what our typical model of the labor market would kind of look like. Now, by contrast, in a model with multiple steady state, we see we have an example here where there's an additional intersection here, this point B. But then when we look kind of at the dynamics around that point in this graph, so we see that this is more like a threshold. If unemployment is sort of below point B, then there's a tendency to revert back to point A, the low unemployment steady state. If you get above, then unemployment tends to diverge to some higher level. So this actually implies that there has to be some other stable steady state to the right here. Okay, so we can kind of think of this area over here as this dark corner that Blanchard is talking about. Okay, so now we know we can write down these models. They've been around for quite some time. However, in quantitative work, they're not very commonly used. So what I'm interested in this paper is to look in the data for the United States and see if there's any evidence in the data that would be in line with this type of model, with this type of sort of view of the world. Okay, so here are some references. So what I'm going to do is two exercises. One is I'm going to estimate a very simple reduced form model of the labor market using data on stocks and flows in the US labor market. And from that I'm going to infer steady states. So this is going to be a very simple model that's going to consist of forecasting equations. Then to complement that, I'm going to take a more structural approach and actually estimate a search and matching model that, depending on parameter values, allows for multiple steady states. So what I'm going to do is I'm going to take sort of the most sort of pedestrian model of the labor market. I would say I could think of the basic Diamond, Morris, and Pistoridis model and extend that to allow for multiple steady states. So in a basic model, there's only a single steady state. The way I'm going to extend that follows a paper by Pistoridis from the 90s in which he introduces losses of human capital during unemployment. So the reason why you can get these multiple steady states out of that is kind of quite intuitive. So suppose unemployment is high, then the incidence of these skill losses is high. So then it becomes less attractive for firms to hire because part of those skill losses is going to follow on the employers. So then vacancy posting goes down, and that will lead to further unemployment and further skill losses. So this is kind of how you can get into this bad steady state outcome in that type of model. But it's all going to depend on parameter values, and I'm going to estimate those sort of from the data. Okay, so now the result of this sort of the two exercises is going to be very sort of much in line. I'm going to estimate one steady state that's stable around 5.5% unemployment, maybe a bit more, and one unstable steady state, so this point B, around 10%. So that implies that at the peak of unemployment during the Great Recession, the US economy was sort of just kind of on the edge of sort of tipping over into this bad region, which implies that there has to be some other steady state. However, the data over my sample is not going to sort of visit this region where this third stable steady state would be. So I'm not going to have much to say about the location of that one.
Sorry, I'm a bit confused. So you find there's three levels of unemployment rate. So what is it to tell us is outcome of unique steady state but fundamental are different versus they're actually multiple steady state under same fundamental? So I didn't get it.
So the equilibrium here is
So
going to be.
empirically, you sort of find three levels of unemployment. So
Yeah,
I'm
yeah.
saying, are they outcome of model with unique steady state but fundamental are different, or is it multiple steady state with same fundamental?
Yeah, it's a latter. It's really a model with multiple steady
So
states.
how do we know that? That's my question.
So you say.
I know you want the second one, but I mean, how do we know?
What is the
But-
identification component?
Yeah, I was just going to sort of talk about that. Okay, yeah. So suppose we would simulate data from these two types of models. Okay, so say we introduce shocks to unemployment. So then what the distribution of unemployment would tend to look like is just kind of a distribution around this long run attractor point, A. So there would be sort of fairly symmetric distribution typically. However, in this multiple steady state world, you kind of, if you once in a while have a shock that kind of brings you close to this point B, then you kind of have, if you look at the dynamics here, the reversion is very slow. So this type of model implies the very large shock may also be a very persistent shock. So you kind of get this second cluster of data points. So if you kind of would look at the distribution, you kind of get this kind of fat tail over here, which is, if we look at the...
Which technically could also be done without a steady state. Just can do like this, and then you're not going to really have evidence on unemployment rates above the other one, because then unemployment rates should have diverged, right?
Right, so then you would have to go to, say, Spanish data or something like that, where you can, but where you do have these extreme unemployment. I'm serious.
Go back to your plots. I was also serious too. What I'm saying is that you're going to be using the fact that to a point relatively far from A, you're going to have a fat tail.
Yeah.
So to me, that's evidence that then the curve kind of shifts backwards. It's not really evidence that it cuts again.
Yeah, so I mean, this is sort of the rough property in the data that's going to give rise to the result. I'm actually going to try to estimate this line. But sort
you're
of,
never going to have actually in your identification and taking it literally with your model, you're never going to have data to the right of point B.
there are going to be a few data points to the right, but only a few during the
shocks.
Then the shocks kind of move you
so
back.
The interpretation will be that you were really, really, really lucky and had the right shocks.
Well, so at this point, yeah, it kind of becomes like a 50-50 type of thing. Yeah. Lucky, yeah.
Okay.
Yeah. Okay, so now let's look at the data. So let's start at the left column here. So this is the job finding rate over the last 25 years for the United States. And what we see is sort of, this is the light gray points are data for the period 1990-2007. So these darker points are kind of the Great Recession and later points. And what we see is we kind of get this additional sort of cluster of...
Sorry, what you have on the axis is...
Oh, sorry. This is the job finding rate today versus the job finding rate 2 years later. 2 years later. Yeah, so this, had to choose something. So you kind of get this cluster of data points where the job finding rate tends to stay at a very low level for quite some time during the Great Recession and after. So if you would look at the distribution of the job finding rate, what you actually get is this bimodal distribution where you have this sort of period of very low and persistent job finding rates. If you look at the job loss rate, you don't really see that. So this looks much more like a symmetric distribution. Finally, you can look at unemployment, which is kind of the convolution of those two. So these three variables are mechanically related, and it inherits some of this fat tail property of the job finding rate, although it's less stark because the job loss rate also kind of kicks in there. Okay. So now let me start with the first exercise, the reduced form model. Think of a very simple 3-equation model of the labor market. There are 3 variables here: unemployment, a job loss rate, or X, and a job finding rate, or F. I'm going to remain agnostic about what is the structure that determines those 2 transition rates. I'm just going to say that there's some function of an aggregate state vector that I'm going to call S. this first equation here is just an accounting identity for the unemployment rate, which basically says that sort of the unemployment rates consist of those who were previously unemployed and didn't find a job, and those who are newly unemployed. Okay, so this I'm going to impose on the data. Right, so now to give you a very sort of simple example about how mechanically you're going to get possibly multiple steady states in this environment, suppose the job loss rate is just some kind of constant, rho x bar, and suppose the job finding rate is some linear function of the unemployment rate. So these gamma 0 and gamma 1 are reduced from parameters that ultimately are determined by the structure of the model. I suppose the world looks like this. Then if we want to solve for the steady state, what we do is we plug those two functions into the accounting identity and impose the restriction that in the steady state, unemployment today is equal to unemployment tomorrow. When we do that, we get this equation over here, and what you see is we get here these quadratic terms. And the reason is that the job finding rate depends on the unemployment rate, and through the accounting identity, the unemployment rate depends on the job finding rate. So you get this quadratic equation which typically has two solutions, right? So this is how you can get mechanically multiple steady states. Of course, it could be that one of those solutions is negative or above 100%, so it's not empirically relevant. That of course is all going to depend on those parameter values, and I'm going to try to learn about those from the data. Okay, so that's the idea. Now, one could sort of try proceed and kind of estimate these sort of type of equations reduced form. The problem, however, is that this state vector S may not be entirely observable, right? Typically, if you think about models, it would include shocks. This could be like demand shock, supply shock, whatever shocks. And we may not know what shocks are sort of the first order shocks that hit the economy. Further, even if we would know what the shocks are, they may be hard to observe directly in the data. So that's kind of the challenge I'm facing here.
So I thought we sort of buy into the constant return to scale kind of setting. So are you saying that over time there is this kind of increase in return to scale by having gamma 1 positive?
In the matching function, you mean, or in?
Or just in the data?
Yeah. So here I'm kind of. I'm going to remain agnostic about that, but there's some mechanism that will indeed create, if unemployment is high, then job finding rates are going to be additionally low. So there's some mechanism. In the model, I'm going to get it from these scale losses. But for example, having non-constant returns in the matching function would be an alternative way of generating it. So, yeah. Okay, so now let me just go on and be a little bit more formal. So the way I'm going to set the model is I'm going to have a vector X of outcomes that I can observe in the data. So those would include those two transition rates and possibly also other variables. I'm not going to include the unemployment rate, and the reason is that I'm going to actually use this accounting identity to solve for that one, although one could add it as well if you really want to. Then I'm going to estimate a k-step direct forecasting function. And what this equation says is just, the only thing this says is just this forecast is just a function of the current state of the economy, which contains all possible information.
Sorry, maybe I'm still confused. If you go back to the previous slide, so I guess what I'm asking is, if you add another variable that's close to the idea of tightness, then you would change your estimate. You know what I mean?
Yeah, there might be maybe other variables in there.
So, are you not estimating this?
No. So this is just an example.
Oh, okay.
This is just an example. I'm going to allow for other stuff. Yeah. Okay. So this forecast is a function of the current state, which I may not be able to observe. So it may consist of partly observed state variables, so those may be lags of variables in xt, and then unobserved state variables. So now the trick I'm going to use is really the point that currently observed variables in x, our outcome variables, are functions of the state. So if we want to make a forecast, then instead of conditioning on this unobserved state, all we need to do is condition on enough currently observed outcomes that are functions of the state. And I'm going to kind of do empirical tests to kind of check that I have enough current outcomes vectors, variables in my model to kind of capture the state of the economy. So that's the trick. So I'm going to replace this S2 by the current vector S. So once I've done that, it's straightforward to solve for the steady state in the same way that I showed you in the example before. Okay, so the data. So they are monthly data from the current population survey starting in 1990. I'm going to have direct measurements for the job finding rate. I'm going to measure that as the flow rate from U to E's, from unemployment to employment. I'm getting those from the gross flow part of the CPS. Then I'm going to take the unemployment rate and construct the job loss rate to be consistent with this transition identity for the unemployment rate. So that's the data. There's an alternative way of getting these data, and then you can actually go back further than 1990. That gives very similar results. But the data, I think, is of somewhat lower quality. Okay, so now, given that this comes from a survey, these transition rates are a little bit noisy, and this may create some attenuation bias. That's why I use lags as instruments to avoid that issue, but it's not really important for the results. Okay, so this is the job finding rate. So the key thing we saw after the financial crisis is that the job finding rate dropped, and then it stayed low very persistently over here. The job loss rate looked quite different. We kind of saw this spike in job losses at the beginning, but then the job loss rate quickly reverted back to its usual level, so there's much less persistence. Okay, let me skip this and tell you directly how I'm going to estimate the model. So the key thing is that I need to include enough sort of variables in my forecast to capture all the sufficiently capture the different dimensions of the aggregate state. So these are kind of three specifications that are going to summarize the main results. I've run many more, but this kind of summarizes things. The simplest one conditions the forecast caper its ahead of the job finding rate just on the current job loss rate and the current job finding rate. So then by construction, I'm not going to have multiple steady state because the unemployment rate is not part of this state here. Right, so that's going to be really key here, whether the unemployment rate is a state variable or not. Because when the unemployment rate is a state variable for these transition rates, then you get these multiple steady states. Okay, so that's what I'm doing in the second one. I'm adding the unemployment rate. And finally, I'm adding the unemployment rate squared. So why unemployment rate squared? Well, it turns out that this equation is going to fit the data a lot better. But also in models with multiple steady states, in order for you to have two interior stable steady states, and then it would be an unstable one, so you would have three steady states. In order to allow for that, you need this squared term. Then I'm going to check sort of which of those three equations fits the data best, and I'm going to have several criteria for that. I did the same thing for the job loss rate, but there I found it's really difficult to improve on just a simple error one, so that I'm not going to discuss here.
So where does that tightness concept
That will be in the model would be in the current row F would be a function of tightness. Like in the basic modus simpliciter model, job finding rate
so
is.
you're saying the future
Yeah.
tightness and current tightness
Yeah.
should be the same.
Yeah. So if we think about a very simple dynamic modus simpliciter model, then tightness is, say, with stochastic productivity shocks, say, then tightness is a function of productivity. And then job finding rate is a function of tightness. So implicitly, job finding rate is just a function of productivity. So that would kind of capture that. So but this is the part that would capture the tightness.
Have you tried adding more lags?
Oh yeah, I mean, I'll come to robustness. I've done a battery of a robustness check, but that's one of the things that
You
it.
can generate multiple steady states also with a lag.
No, I think you do. Well, with lags of unemployment, but without having unemployment, then you can't get it. Yeah. You really need unemployment in there.
And how does the job-to-jobs transition?
Um,
There's a different job-to-jobs transition over time.
Yeah, so I don't use any data on job-to-job transitions in this. So I'm kind of sticking to the very simplest world where they just transitions between employment and unemployment. I think one could think of many interesting extensions where you would have job-to-job transitions and out of the labor force into labor and so on. I'm going to stick to sort of the simplest case.
But how would it affect the result if they were? How might?
That's a good point. I could actually, I could just empirically, I could just add it. I could check that. I don't know. Thank you, Albert. Okay, now I want to sort of choose between these different specifications, and the key criterion for that is to look at autocorrelation in the residuals of those forecasts. Why is that? Well, if we are missing some information about the aggregate state, then this will show up as autocorrelations in these forecasting errors, basically, right? Then you're really missing a variable. So when we look at the baseline model, the simplest one, that's the blue line, we see that for a whole range of forecasting horizons, plotted on the horizontal axis, we get these pretty big autocorrelation in the residuals of almost a half. So these forecasting horizons correspond to individually re-estimated models. Right, so this model clearly seems to lack some important information that's relevant in forecasting and therefore an important part of the aggregate state.
From 1990
yeah.
to 2014.
Yeah. I have an extension going back to 1960, but this is starting in 1990. Yeah. Right. So then the second one, adding unemployment helps a little bit in alleviating this problem, but it still is a misspecified model as judged by the autocorrelation in the residuals. By the way, so here I'm checking, because I'm having multi-step direct forecasts, you kind of get mechanical autocorrelation in overlapping forecasts. So here I'm only looking at a non-overlapping forecast. So that's an aside. We can also look at the R-squared, and we see that the third specification also improves a lot the accuracy of the forecast. So based on these two plots, I'm going to use this third model as baseline. So I've tried adding various other higher order moments and variables that sort of had very little effect. So I'm going to show you results for this specification. Okay, so now we can look at.
Does this depend too much on putting the data after 2007?
That's quite important, yeah, because that's really, in this data sample, that's really the only period when we get these data points of close to 10%. Oh, that I haven't.
It's maybe really driven by that one episode you have in mind.
Right, so we do starting from
I'd
the.
be more convinced if you could cut the sample somehow in 2007 and still convince me that the quadratic is.
Right, so then it would be the 1980s recession. That's because otherwise there's just not that many recessions that are sort of sufficiently big to get close to that point. Yeah, that's a good point. Okay, so now I can look at the results. So these panels correspond to different forecasting horizons. So this is 6 months ahead, 12 months ahead, 24 months ahead, 36 months ahead. So let's focus on the red lines, which this plot is kind of the equivalent of the illustration I showed you at the very beginning. So unemployment today versus.
So you're doing the best parameters for the 6 period horizon. Then you check with the best parameters of the 12. Why do we get 4 different?
Oh, it's in a way it's sort of a robustness check. I can do this for any forecasting horizon.
So because you do it for different forecasting horizons, you get different parameters. You use those parameters to compute.
To compute the steady state, and hopefully those should be the same if the model is correctly specified. So yeah.
Okay.
So the shapes of those curves, those naturally depend on the forecasting horizon. However, the steady states of the model should be the same. So the steady states would be, again, these intersections with the 45 degree line. And it turns out that across these forecasting horizons, it's quite robust to get or very robust to get an intersection around 5.5%, and one somewhat close to 10%. Yeah.
Yeah, probably should have asked that way before with the model, but is that a feature of that Pizzerides models that you're looking at? That because in many models, I think if you say you have 2 aggregate states, then this mapping from UT to UT plus 1 would shift, right? And the way you wrote your equation is that it's the same mapping plus some error, right? Is that a feature of that model, or is it?
Should we say if you add multiple aggregate shocks?
So I could imagine many models where you have 2 aggregate shocks, right?
Yeah.
And I would guess that there is one transition equation for the low shock and another one for the other one, and you would have 2 of those transition lines, right?
Yeah.
But that doesn't seem, so the way the pictures you're always showing is one line, right? One
Yeah. So the way to interpret those lines is sort of setting the shocks to their steady state level. So just focusing on the deterministic dynamics of the model.
So that's good.
Yeah.
That's a good approximation of the.
Yeah, I think that's we'll see later. So I'm going to set up these search and matching, but that's consistent with the model. Yeah. Okay, so these are the robustness checks. Yeah, let me just.
Can I?
Yeah.
Maybe I should have asked this before too. So, do you have an R1 process for the job finding rate?
Yeah. So
in these estimations, right?
yeah. So the only point in which I'm going to use is to construct those steady state curves. I set the job finding rate at the average level. So it could also be some other process as long as there's sort of no nonlinearities in that.
What I was wondering, so is the shocks that are in principle embedding this rho x independent of the shocks of the job loss?
So can you say that
You
again?
have two shocks, right? So you have the shock in model 3, let's say model 3,
Right,
the one
yeah.
that we like, and then you have an R1 process for this one.
Yeah.
Not to plot in this graph, but
Yeah.
with the estimation it is, right?
Yeah.
In the estimation it is. Are the shocks independent? I'm wondering whether, if you had a negative correlation that could help you, perhaps even to accept model 2, meaning like the persistence that you have on the epsilons, on those ones.
Right.
Left graph. If you had a negative correlation, wouldn't that help you get rid of that persistence? Negative
I don't think so, because like the way I'm going to set up the model, there will be a shock to rho x, but in a way you're kind of conditioning on that shock by having this by conditioning on rho x in the forecasting equation. So that's kind of so I'm not sure. I don't think I.
Maybe we can talk about it.
Yeah. Okay, so once you've estimated the model, you can make a phase diagram. Usually we do this for theoretical models, but you can do it for the empirical model as well. Let me just, it takes a little bit of time to explain exactly what this is. But we have the unemployment rate here and the job finding rate here, and we kind of have different regions with different forecasted motions of direction, and we can kind of construct this region of the current variables where unemployment is not forecasted to go back to this low unemployment steady state, but instead diverge. And we kind of, these dots plot the actual data points, and at the peak of unemployment during the Great Recession, you kind of get at the edge of that region. Okay. So now let me instead go to the search and matching models. I'm going to estimate two models, basic Morrison-Pisaridis model with a single steady state, and then I'm going to have this extension a la Pisaridis 92. This is going to have multiple steady state depending on parameter values. It's always going to have a unique dynamic equilibrium, so there's not going to be any room for sunspots or anything like that in this type of model. And there's going to be one parameter that's going to determine the extent of these scale losses, and when I set that to 0, it basically nests the Morrison-Pisaridis, the standard diamond Morrison-Pisaridis model. So it's kind of a fairly minimal deviation in a sense from the standard model. The only shock I'm going to have in the model is a shock to the rate of job loss, which I'm going to take as exogenous. I'm not going to have anything to say about that. I'm just going to take that from the data. Timing of the period. So first job losses take place at the beginning of the period. Then those who do not have a job, they search and they find a job at the probability rho f. This is because firms post vacancies denoted by V and they come at a cost kappa, and they're filled with a probability Q. Then in the third stage, production and consumption takes place. So the workers who have a job, they produce some amount A bar, and those who are unemployed, they get some amount B from home production.
So the only feature of a recession is the higher separation rate.
That's going to be the only shock, yeah. In my quantitative exercise, of course, you could add other shocks as well. But the surprising thing is going to be that with just that shock, you can actually do pretty well. And the advantage is that it's a shock that I can take directly from the data, basically. I don't have to rely on some unobservable shock. Okay, so then the key addition to the model is this introduction of human capital losses. So in this model, when you lose your job, you may immediately find a new job at the beginning of the next period. So you would transition between jobs without actually becoming unemployed in this model. Then I assume you keep your human capital. However, if you're unemployed for at least one period, then you lose some human capital, which means that if you would get a new job, your employer would have to train you to make you suitable for employment again. And this would require some cost chi. So by setting that chi to 0, we get the standard modus simpliciter model. Okay, so now what the firms are going to care about, given that search is random, is that the fraction of the people they're going to hire who is going to have to be retrained, who have lower human capital. And that's this variable P. So it's those who were previously unemployed divided by the total pool of job searchers, which is the previously unemployed plus the newly unemployed. So this is exactly why unemployment is going to be a state variable in this model, because the firms kind of care about this P, which it depends on U. When I strip the skill losses out of the model, the unemployment rate is not going to be a state variable for these transition rates. Okay, so here we get the vacancy posting condition or the free entry condition. It's quite intuitive. So on the left-hand side, we have the cost, the expected cost of hiring a worker, which is the vacancy cost divided by the probability of filling a vacancy. And then on the right-hand side, we have the expected value of profits. So the wage is W, so A minus W is the profit you make out of a worker. So it's the expected value of those profits, taking into account that each period the match separates with a certain probability. And then an additional cost component is that some of a fraction P of the new hires you're going to have to retrain. So you have to pay this chi. So now this D here, that's a potential discount that the worker may accept in their wage, in their initial wage, to kind of share in some of those retraining costs. This is something that would arise from Nash bargaining. It's not going to be important in my quantitative application. Okay, so the matching function is a standard Cobb-Douglas function of the number of searches S and the number of vacancies. For simplicity, I'm going to assume sticky real wages. So the firms are going to have all the bargaining power, so W is going to be equal to B, and as a result, this discount is going to be equal to 0. With flexible wages, you can also get these multiple steady states. So in that sense, it's not crucial. Okay, so we can summarize the model. So and it actually has a very similar structure as this reduced form model that I wrote down earlier. So this is this accounting equation again. Then this is the AR1 process for the job loss rate, which I'm just going to estimate from the data. And finally, we have some equation, which is just a free entry condition, which I rewrote to express it recursively, which one can actually think of as a one period ahead forecasting equation for the job finding rate. All right, so now the key thing is that as long as this chi, this job loss, human capital loss parameter is bigger than 0, then the unemployment rate is going to be a state variable here for those transition rates, but it's not in the standard model.
What's the bargaining power for the employer?
So here I'm going to give all the bargaining power to the employer. So it's just going to be a sticky wage model.
Okay, so wouldn't the DT take care of the DT that is being paid by the worker? What is the equilibrium DT?
Yeah, so I've worked out those cases. So then in the DT, yeah, that's going to be 0.
Even
here.
if the employer has
so
the bargaining power?
Yeah. You can show that, yeah. Alternatively, you could just assume that the worker, the employer has to pay for it, but I show it in the paper. Okay, so now to parameterize the model, I'm going to assume a discount factor that implies a 4% interest rate on an annual basis. The matching function elasticity I'm going to set 0.6, which is the midpoint of a range suggested by a survey paper by Petrolongo and Pissarides. Worker productivity I'm going to normalize to 1. The other parameters of the model I'm going to estimate. So these are the parameters pertaining to the exogenous job loss process. So there I'm just estimating a simple AR1 process. nothing special here. The other parameters I estimate using an indirect inference procedure. So the way I'm going to do that is I'm going to search the parameter space, and for given parameter values, I can search a simulated model. I solve and simulate the model, taking the initial conditions for the data from the data, and simply fitting in the job losses that I get from the data. So from that AR1 process, I can construct the shocks that are needed for the model to exactly coincide with the data in terms of the job loss rate. Right? So that's I'm going to feed in, and I'm going to ask to what extent the model can reproduce the job finding rate that we see in the data. So now I'm going to choose parameter values such as to minimize the root mean squared error of the job finding rate in the data minus the job finding rate that's simulated by the model. So that's the headed job finding rate here. I can redo this, setting this chi to 0, so that would be estimating the basic version of the model with a single steady state. So the question then is, of course, are these parameter values that I'm going to estimate implying multiple steady states or not? Okay, so these are the parameter estimates. So this is the baseline model with skill losses. The most interesting one is probably this estimate of this retraining cost. So that's 0.66. So this implies that the degree of human capital losses boil down to 2 to 3 weeks of output of a worker. So I would say that's a fairly small number. It's certainly not very big. Okay. So I re-estimated the model without skill losses, then I set that chi to 0, and we can kind of look at how well these models do. So these are the root mean squared errors that I get out of them, and we see that indeed the model with skill losses substantially improves in terms of the model fit over the model without skill losses. And in fact, the model without skill losses does almost as well as a model where I'm just setting the job finding rate to be constant over the entire sample. So it's really not much of an improvement there. Okay, so let me show you what simulations are underlying that result. So these are the job loss rates. They are the same for the models, and I'm just taking them from the data. So we get this spike at the beginning of the Great Recession. This is the job finding rate that's endogenously generated by these models. The blue line, that's the data. The red line is the model with skill losses, and the green line is the model, the basic Morris and Pissarides model. Right? So we see that these job loss rate shocks in the basic Morris and Pissarides model, even if you kind of estimate the parameters to make the model fit the data as well as you can, really don't generate a lot of fluctuations in the job finding rate. Whereas the model with skill losses tracks I would say, the data surprisingly well. In particular, we know that this wave of job losses was not very persistent, but the model is able to generate this very persistent fall in the job finding rate. And this really comes from an endogenous propagation mechanism in the model. If unemployment rate is high, then these skill losses are high, so vacancies are going to be low, and this is kind of going to persist. So this is the reason where we'll see in a minute, you're going to be kind of close to this unstable steady state point.
Why does it look a little bit lag?
Sorry?
Why does it look a little bit lag?
The red. Because here basically when the job loss shocks hit, then for these skill losses to accumulate, it takes a little bit of time. So that there's sort of kind of a couple of periods. So I think one could. I have some ideas of how one could kind of bring that closer. But it's basically because this propagation mechanism takes a little bit of time to kind of realize. But the other thing is, the other thing is that you kind of, you start off from a higher level here, basically. Yes. Sorry, go ahead. It's not always lagging. Yeah, sure. This is the implied unemployment rate, which is just mechanically the result of these job loss and job finding rates. The basic Morris and Pissarides model does generate some increase in unemployment, but that just comes mechanically from the increase in job losses. Right, so it doesn't come close to the data. Okay, right. So, so now we can use the model and sort of estimate what are the implied steady states by these two models. In the model without skill losses, there's going to be only one steady state, and that's by construction, which the other model estimates to be at 5.9%. Now the model with scale losses generates these two steady states. So one with a stable steady state at 5.75% unemployment, so a little bit higher than the estimate from the reduced form model, but still pretty close. And then the unstable steady state point is estimated to be around 10.5%, so a little bit higher as well than in the reduced form model, but still pretty
But this
close.
is assuming the whole period. The only thing that changes is the job destruction rate.
Yeah.
And all the other parameters like skill loss, how frequently you lose skill, all these things do not change, right?
Yeah.
So it doesn't answer the first question. It's like, you know, whether it was a change in fundamental give you different.
Oh, okay. Now again,
Unemployment rate, or is it the same fundamental give you multiple steady states?
right? Yeah.
It's very difficult to show that there's multiple steady states.
Right. So I think so. Yeah. So you could, if parameters of the model, fundamental parameters of the model
Like, for
change, you can get a
example,
different state.
You know,
Yeah.
Jonas and Lucas talk about turbulence, so that means low skill has been bigger, so the chi is
Right.
bigger. So if you separate the sample and estimate it differently, you know. So I don't know
Yeah.
how to think
So
about it.
I think one thing that really speaks in favor of the multiple steady state view of thinking about it is that this sort of transition here occurred sort of very fast. When we think about parameters of the model changing, then typically that's something that, you know, happens sort of gradually over maybe a couple of decades. Here it's just, it's not like a downward trend, it's just something that happened right over here. So I think that's something that's like unless you're going to assume that parameters all of a sudden change, I think that wouldn't be so plausible. So that kind of speaks for the multiple steady state way of thinking about it here.
You have 3 minutes. You have to choose how to
All right.
use them.
Yeah, so let me just illustrate just a deterministic simulation to show sort of how different those two models are. So I'm not considering any shocks here. I'm just setting the initial unemployment rate to around 10% and just simulate both models. So in both cases, we're just below this unstable steady state point. So we are going to go back to the low unemployment steady state. However, we see that the model with skill losses has basically very little endogenous persistence in it. So very quickly you get back. Whereas the model with skill losses has a lot of endogenous persistence, and that's exactly the feature that helps it to explain this very persistent job finding rate following the Great Recession. Okay, I think I'm actually done. So I showed some evidence that this multiple steady state view of the world, so this type of models, even though we don't use them very often quantitatively, could be really quite promising in terms of fitting the data. I've estimated this dark corner region where things may get really bad to be sort of around 10%. I didn't talk about policy because obviously that's going to depend on the particular mechanism that generates those multiple steady states. But I think one thing that class of models has in common, that policy implications, the effects of policy can be very large and nonlinear, especially if you have a kind of a policy that kind of pushes you from the bad into the good region. Yeah.
So can I ask?
Yes.
Sure.
I think you have to be a little bit more careful. Say basic EMP model, Mortensen would have been very upset. You know, the whole point of Mortensen was to have endogenous destruction.
Right.
And you know, that was just already removed, and then to say, oh, that model is better than EMP. You know, I don't know if you can just put the endogenous destruction in, and then run the race again for these two models to see. You know, I think we might still hold. You know, what you find might still hold, but you know, at least it's a more proper way
Yeah.
to say.
Okay, so I think the better way to say it is the simplest version of that model I could personally think of. But I mean, I agree. So you could do that, yeah, sure.
Pizzerilli 92 is better than Pizzerilli 85. That's basically what you did there. Model you
Sure,
have is
yeah,
92 versus 85,
yeah.
not EMP. But I think the persistent, you know, still is not really a justification for the multiple steady state. I'm sure you can add other things into the model to get persistent.
Yeah, yeah.
But what you were saying to me, like, you know, when I had that match quality persistent thing, I also get a a lot of persistence.
Yeah, so it's sort of two
So-
things.
so-
This one is persistent, but the other thing is that a big shock has also very persistent effects. And for that, you really need the
Yeah, you
nonlinearity.
can still get it in the setup I have with that persistent. So that's why I don't think it is an answer that therefore we need multiple steady states. So something more need to.
Okay, let's talk about it.